YouTube video about the Bergeron process, which, as we all know, is probably the most challenging concept that we deal with in Weather and Climate and Geography 1250 during the course of our semesters. So hopefully this video will be a nice study tool for you for both Exam 2 and the final exam. So it covers about 12 slides of our unit on fogs, clouds, and precipitation. So let's get started and let's take care of the Bergeron process and ice in the atmosphere. So the last thing we talked about in this presentation was the formation of precipitation in a warm cloud via collision and coalescence. But as I noted in class, water is a pretty complicated bit of business because it is the only substance in nature that can exist in all three phases at the same time. So what we're going to be talking about now is how we actually form precipitation in a cold cloud or a cloud where the temperature has a temperature less than 32 degrees Fahrenheit. So the question that we have to answer is, how do we get from a liquid droplet in the atmosphere to an ice crystal so that it can snow, basically? So let's start with a cold cloud. So a cold cloud, by definition, is going to be a cloud where the air temperature is less than 32 degrees Fahrenheit. And what we're going to see is that in a cold cloud, the cold cloud is going to contain water vapor, and it's also going to contain ice crystals, as well as droplets. So water droplets can actually exist in the liquid phase at temperatures less than 32 degrees Fahrenheit. And so these are supercooled water droplets. And so remember that we can actually have droplets in the atmosphere, liquid in the atmosphere, because these very tiny droplets have very sharp curvature on their surfaces, and so that surface tension actually creates enough tension for them to stay in the liquid phase at very small sizes at temperatures that actually can get down to 40 below zero Fahrenheit, which, by the way, is also 40 below zero Celsius. And so it turns out that all liquid water, regardless of the size of the droplet, has to freeze at a temperature of 40 below zero Fahrenheit and Celsius. So it turns out that negative 40 is the actual freezing point of liquid water. So in order for us to get an ice crystal in the atmosphere, just like with water droplets and condensation nuclei, ice crystals have to form on something called deposition nuclei. And deposition nuclei are kind of specialized. They have to be hexagonal. They have to be six-sided. So deposition nuclei are six-sided, and they're relatively rare in the atmosphere. So because deposition nuclei are rare and condensation nuclei are really, really abundant, it turns out that most of our cold clouds are composed almost entirely of supercooled water droplets, in spite of the fact that the temperature is less than 32 degrees Fahrenheit or 0 degrees Celsius. So if we have a cloud that is composed primarily of liquid droplets, how do we actually get this cloud to produce snow? And that's what's going to lead us to the Bergeron process, this process by which we end up growing ice crystals and get snow formation in a cloud that begins being comprised entirely of supercooled water droplets. So let's start with just beginning to develop our variables for the Bergeron process. And so I'm going to start with the saturation vapor pressure of air around ice, or E sub SI. E sub SI, the saturation vapor pressure of air around ice, basically tells us the maximum amount of vapor that can exist around an ice crystal at a given temperature. And when we have equilibrium around an ice crystal, what that means is that the rates of sublimation and deposition are equal around that ice crystal. In better words, the amount of molecules that are going from the solid to the vapor phase is equal in terms of the rate of molecules that are going from the vapor phase back to the solid phase. Now, these phase changes are occurring at very low temperatures, and a lot of energy is required to both sublimate and deposit water. And so this process is actually quite slow. And so what we're going to see soon enough is that the saturation vapor pressure of air around ice crystals is actually fairly small because of the energy level of the water molecules around an ice crystal. On the other hand, we've already dealt with, in our PowerPoint and in this unit, the saturation vapor pressure of air around liquid water droplets, or around liquid water. So when we get equilibrium, the rates of evaporation and condensation around the droplet are the same. And so if we're in equilibrium, if the relative humidity of the air is 100%, the rate at which water molecules are evaporating from liquid to vapor is equal to the rate at which vapor molecules are condensing back into that liquid droplet. Now, what we see in our cold cloud, where the cloud is comprised primarily, almost entirely, of water droplets, we have to have an environment where those water droplets can actually exist, or we won't have a cloud. And so what we see in a cold cloud is that the air has to be in equilibrium or saturated around our water droplets. And so what we have here on the right-hand side is basically our diagram of vapor pressure on the y-axis and temperature in degrees Celsius on the x-axis. And these are our saturation vapor pressure curves for liquid water, so this is the red curve, and for solid water or ice, and this is our blue curve. And what you see, and we're just going to stick with looking at 20 below 0 Celsius, which is about 4 or 5 below 0 Fahrenheit. So what we see is that if we go from the bottom of our diagram where the vapor pressure is 0, and we actually increase the vapor content of the air, what we see is that the air becomes saturated around the crystal, or it gets onto the blue curve, at a lower value than it is for the red curve. So this basically means that more vapor is required to saturate the air around a water droplet than it is to saturate the air around an ice crystal at the same temperature. So given a single temperature below 0 degrees Celsius, what we see is that the air has two different saturation vapor pressures, one around ice, which is relatively small, and the second around liquid water, which is relatively large. So within a cloud, we need to make sure that we're clear about what goes on inside of a cloud. And inside of a cloud in the real world, we can pretty much assume that the cloud has just one temperature, somewhere less than 0 degrees Celsius, but above 40 below 0 Celsius. So the cloud has just a single temperature in the negative digits, and the cloud has just one actual vapor content, just one E. And what we see in the cloud is that the vapor pressure of the air, the actual vapor content of the air, indicates that our vapor pressure is going to be pretty much on the saturation curve for liquid water and above that for ice. So in a cloud, what we're going to see is that we have one temperature below 0 Celsius, one actual vapor content, and in our cloud, in any cold cloud, we're going to see that for this given temperature, the saturation vapor pressure of the air around liquid droplets is going to be greater than the saturation vapor pressure of the air around the ice crystals. Now, before I move on to the next slide, I just want to point out that if we take a look at the opposite ends, the extremes of our curve, so on the cold end at 40 below 0, and on the warm end at 0 degrees Celsius, you can see that the curves actually meet. Now, on the warm end at 0 degrees Celsius, the saturation curves for ice and liquid meet because at this temperature, ice has to melt. And so if we actually look at values warmer than 0 degrees Celsius, we would just have the red saturation curve for liquid water. On the other hand, they meet again at minus 40 because this is the temperature at which all liquid has to freeze. And so again, the two saturation curves meet. And if we continue to the left at temperatures lower than 40 below 0, all we would have is the blue curve because we would not have any liquid water droplets. So just to specify why it is that this diagram looks the way it does. All right, now what we see in a cold cloud is because we only have one temperature and we only have one actual vapor content, what we see is that in order for us to actually have a cloud, the air around all of those liquid water droplets has to be saturated. That's the only way that the water droplets can be able to exist because we don't allow supersaturations, at least around liquid water. So we require that the air, at least to begin with, be saturated around all of our water droplets so we can have a cloud. But then what we see is that while the air around the liquid droplets is saturated, the very same air, same temperature, same vapor content, that very same air is going to be supersaturated around a couple of ice crystals that we have floating around in that cloud. And so this is actually the setup for the Bergeron process. And what the Bergeron process basically does is it tells us that we have this tension between equilibria. So given one temperature less than 0 degrees Celsius, the air can be in equilibrium only around a droplet or an ice crystal, but not both. Not both. And in this case, what we see is the air is in equilibrium around the droplets, so the rates of evaporation and condensation are equal, but we have a supersaturation with the same characteristics around our ice crystals. So while ice and supercooled water can coexist in the cloud, only one of them can be in equilibrium given a single temperature and vapor pressure. So if the actual vapor content of the air is equal to the amount required to saturate the air around ice crystals, and this is what I'm showing in the right-hand figure, I have our asterisk on the saturation curve for ice crystals. If this is the case, what we see is that the air around the droplets has a relative humidity less than 100%. In better words, the amount of vapor required to saturate the air around droplets is greater than the actual vapor content. So the air is subsaturated around the droplets. So what we see is that this very same air is in equilibrium around our ice crystals. We have exactly the amount of vapor in the air that we need to saturate the air around the crystals so that the rates of deposition and sublimation from that crystal are identical. And in this case, what we would see is that our crystals would be in equilibrium, but our droplets would evaporate because the air around the droplets, this very same air around the droplets, is subsaturated. On the other hand, if the actual vapor content of the air is the amount required to saturate the air around the droplets, then our droplets will be in equilibrium and the rates of evaporation and condensation will be equal. But this very same air around the ice crystals has more vapor than is required to saturate the air around the crystals. And so the air that is saturated around the droplets will be supersaturated around the couple of ice crystals that are floating around. And so the relative humidity of the air around the droplets will be 100%, and the droplets will be in equilibrium. The rates of condensation and evaporation will be equal. The very same air around ice crystals will have a relative humidity greater than 100%. There will be a supersaturation. In better words, the rate of deposition of vapor onto the crystal will be greater than the rate of sublimation from the crystal because there's an excess of vapor surrounding the crystal relative to what is needed to be in equilibrium. And so in this case, the ice crystals would grow via deposition. Now this, with my rotating snowflake, this is what we see in the real world. Because in order for a cloud to exist, in order for a cold cloud to exist, the air has to be in equilibrium around the droplets. And so what we see in the real world, at least to begin with, is that the asterisk is on the saturation curve for water. So the actual vapor content of the air in the cloud is going to be equal to the vapor required to saturate the air around the water at this one temperature below 0 degrees Celsius. And that brings us to the Bergeron process. So the Bergeron process basically begins with where we ended on that last slide. And that is, we're going to consider a cloud where the temperature is somewhere between 40 below 0 and 32 degrees Fahrenheit, and where the actual vapor content of the air is equal to the amount required to saturate the air around our liquid droplets. So in this case, the relative humidity of the air around all the droplets will be 100%, and the relative humidity around the couple of ice crystals floating around will be greater than 100%. So what we're going to see in this case, and this is the first step in our Bergeron process, is that the excess vapor is going to begin to deposit onto the ice crystals, and so the crystals are going to grow. And because we're losing vapor in the cloud, because this excess vapor is beginning to deposit on our crystals, the actual vapor content of the air, E, is also going to decrease. In other words, the mixing ratio, the measure of the actual vapor content, is going to go down. So this brings us to the second step in the Bergeron process. Now what we see is that our asterisk or our dot has moved basically kind of halfway between the saturation curves for the liquid water, the supercooled water, and the ice crystals. So what we see here is that we don't have an equilibrium around anything. The air is basically subsaturated around the droplets. In better words, the actual vapor content is less than what is required to saturate the air around the droplets. At the same time, the air is still supersaturated around the ice crystals. The amount of vapor in the air still exceeds what is required to saturate the air around the ice crystals. Now you'll notice that the supersaturation around the crystals decreases. In better words, the dot or the asterisk begins to move down toward the saturation curve for the ice. And so what we see is that the air around the droplets is going to be subsaturated. The relative humidity of the air around the liquid is less than 100%, while the air around the ice crystals is greater than 100%. So the crystals are going to continue to grow, but their rate of growth is going to decrease because the supersaturation is smaller than it was in the previous slide. On the other hand, the cloud is full of droplets, and so all of these droplets are now going to begin to evaporate, and they're going to quickly flood the air with vapor. So E is going to increase, and what we're going to see in our next slide is that the asterisk is going to pretty much bounce right back up to the saturation curve for the liquid water. So this is now steps 3 and 4 of the Bergeron process. So again, given a cloud where the temperature is between 32 and 40 below, we basically are where we started a couple of slides ago. And so the vapor pressure, the actual vapor content of the air in the cloud, bounces back to the amount required to saturate the air around the droplets, same as 1. So the air again becomes saturated around all the droplets. The supersaturation bounces back up again for the ice crystal, so the supersaturation increases. And we then see that the excess vapor deposits on the crystals. Crystal growth increases in terms of its rate. And so we're going to again begin to remove vapor from the air in the cloud. And E, or the actual vapor content, is again going to decrease. And what's going to happen is we're just going to basically repeat steps 1 through 3 until all of the liquid water in the cloud has evaporated and the excess vapor has deposited onto the ice crystals in the cloud. So Bergeron step 5 is, again, starting with our conditions, we're going to see that the asterisk actually drops down to the saturation curve for the ice. And so that once we run out of liquid in the cloud, there's no more excess vapor to keep adding to the cloud every time water begins to evaporate, because all the water has evaporated. So the relative humidity of the air around the ice equals 100%, and there's no liquid water now in the cloud for there to be a second relative humidity. And so deposition rate and sublimation rate will now be equal, then the crystal growth will stop. And so we're basically done with the Bergeron process at this point. Now that doesn't really necessarily get us to snow, but what we see here before we actually get to how we actually receive snow is just to define the Bergeron process. And so the Bergeron process is the process by which ice crystals grow at the expense of supercooled water droplets in a cold cloud. So this is kind of a simple graphical depiction of what goes on in a cold cloud. So you've got a crystal surrounded by a lot of droplets, you've got a supersaturation around the crystals, and you've got equilibrium around the droplets. The crystals begin to grow, they remove vapor from the air, so the droplets begin to evaporate, which then, pumps up the vapor level again, and then this whole process just repeats. Now I want to make it clear that we don't end this process with just 3 or 4 crystals floating around in the cloud. And I talked about this in class. What happens is that you have to remember that these crystals are incredibly fragile. They're very, very frail. They're super thin. And so what happens is that the air, just the movement of air in the cloud, or the crystals bouncing into other crystals or droplets, what will happen is these crystals will shatter in the cloud. And as the crystals shatter, they shatter into fragments that are also going to be hexagonal. So when an ice crystal shatters, all of those hexagonal fragments act as deposition nuclei. So the crystal then seeds the cloud with more hexagonal deposition nuclei, and then they begin to grow by the Bergeron process. And as they grow, they eventually will shatter and create more hexagonal fragments, and they will act as deposition nuclei, and they will grow by the Bergeron process, and so on. And so the Bergeron process is an extremely efficient process. And so you can take a cold cloud that is comprised almost entirely of liquid droplets, and in a matter of just a few minutes, this cloud can begin to produce snow. So it happens quite quickly. It's very, very efficient. And so here are just a couple of pictures that I've ripped from the internet, but we're educational, so hopefully they won't sue me. So here's an example of an ice crystal in a lab setting, and it's surrounded by supercooled water droplets. And so what you can see is this crystal is kind of growing, and the droplets around it are disappearing. And so the droplets are evaporating, and then the excess vapor is depositing onto this growing ice crystal. Here's a really beautiful picture of an altostratus cloud and some ice crystals that seeded this cloud, and then the Bergeron process basically occurred, and basically all of the liquid in these clouds evaporated. And remember, these are cold clouds. They have to be cold clouds. So all the liquid evaporated, and the ice crystals grew. And what you end up with here is a cirrus cloud, where once you had this mid-level stratus deck. And so this is a really nice example of how sort of this isolated seeding in a cloud actually led to the Bergeron process in a cloud where the temperature was less than 32 degrees Fahrenheit, and then the supercooled droplets evaporated as the ice crystals grew. And then here are some beautiful photos of clouds where you can see that these clouds have a lot of definition. These clouds are primarily supercooled droplets, but we have Bergeron process going on within it, and so we have snow falling from these clouds. One picture, and then an even more beautiful, dramatic picture right here. And this last, I believe this is the last slide in the presentation, just to let you know that there are differences in the saturation vapor pressures around liquid water and ice. And so the difference between the saturation vapor pressure for liquid water and ice is not always going to be a constant value. So what you see at 0 degrees Celsius and 32 degrees Fahrenheit is that the saturation vapor pressures are the same. And when you go down here to 40 below, you can see that they're almost the same. There's a little bit of a difference. But what you see is that in between 0 Celsius and minus 40 Celsius is that a gap opens up in the values of our saturation vapor pressures. And if you look carefully, and I have it pointed out here, there's actually a maximum difference that occurs between around 10 and 15 below Celsius or 5 and 14 degrees Fahrenheit. And where you get this largest difference in saturation vapor pressures between the supercooled water and the ice crystals is where you get your most rapid crystal growth in a cloud. And I talked about the dendritic growth zone in a cloud. So the dendritic growth zone in a cloud is where you have upward motion so that you're getting expansional cooling and condensation onto condensation nuclei, feeding the cloud so that it continues to be able to produce precipitation. And so if you actually get upward motion in a cold cloud within a region where the temperature is between 15 and 20 below Celsius or 5 and 4 below Fahrenheit, this is where you're going to actually get your most rapid ice crystal growth. And again, meteorologists refer to this as the dendritic growth zone. And this gives you an idea of the types of ice crystals that form in a cloud based on the temperature. So based on the temperature and the saturation vapor pressure differences, you get different kinds of crystal formations, although they're all six-sided. So you can get plates or dendrites, you can get columns or needles, but you get your biggest dendrites and your biggest flake formation in the dendritic growth zone. So again, this is basically, again, between minus 10, minus 15, maybe 20 below 0 Celsius. And again, if meteorologists see in models as we're predicting winter weather, if we see that there's strong upward motion and therefore a lot of condensation going on within the dendritic growth zone of a cold cloud, this is an indication that the cloud is going to be a fairly efficient producer of snow that's going to have a fairly large snow water equivalent. And so we get more accumulation when we get ice crystal formation in this zone of the cloud. Okay, and that is pretty much everything I want to say about the Bergeron process. So I'm going to end this video now, and I'll post it on YouTube for you to view, and I'll post an announcement on our website when it's all ready for you. But again, if you have any questions about the Bergeron process, feel free to ask me in class leading up to an exam or during an office hour for either me or one of the assistants, and we'll be able to help you with it. But that's it. That's all for now. I hope this video is of help to you.